Next slide. Yeah, by us as consultants and dam owners to actually put these technologies into practice, that we can develop these technologies further. So I'm not going to say much. I'm just going to introduce the speakers. I have one slide just showing some examples of what we're going to be talking about today. Yeah, the pointer. So yeah, so there's a lot of trending technologies out there. I'm going to let the presenters speak for themselves, but you can see some of the examples here. Ranges from fiber optics that we heard more about yesterday. I guess it depends whether you put that into established or trending. It is definitely trending in some sense. But there's a lot of things to think about when using these technologies, and I think the presenters today will touch upon some of those aspects. So why do we want to use these technologies? They have a lot of opportunities. They can sort of see into the dam, which we can't do. That also goes for the drones that we looked at yesterday. There's a lot of opportunities for continuous monitoring that we can't necessarily do with conventional technology. So that's continuous both in time, that we get through Internet of Things and other things, we get data points coming in at certain intervals, but also continuous in space, like fiber optics. You can measure kilometers of tailings with this one cable. It fills in the gaps of our conventional instrumentation. And a lot of these technologies have the potential through these features of continuity to fill into tarps and early warning systems and emergency preparedness. But we also have to remember that any monitoring infrastructure is an asset, and we have to treat it accordingly. So we need to make sure we have all the documentation in place, all the maintenance, all the support, troubleshooting, etc. That needs to be taken into account. And also we need to, as I mentioned yesterday as well, handle these very large amounts of data that are coming in. And it's not a trivial task to set up your organization to actually handle and make sense of all these data coming in. So with that, we're going to go to the first presenter. That is Simon Steffen from Elexon Mining. I believe he is online. Good. Is he online?
Yeah, thanks.
If he's not there, we will go to the next.
Need to go with Greta, perhaps. Because,
all right, we'll do Greta first then. So next is Greta Tresoldi from LSE Lastem, and I guess you got an introduction yesterday, so I will skip it now. Welcome, Greta.
Thank you.
Gonna do that. Greta doesn't want to load the other way. Right?
Okay.
Yes, try again.
Okay.
Here we go.
Oh, perfect. Thank you very much and good morning. Today I will have a presentation on ERT monitoring, so electrical resistivity tomography for estimation of water content in tailings dams. So we are in the field of geophysics, so we are speaking about indirect measurements, and the methodology is electrical resistivity tomography. So this method is based on the electrical field propagation on the subsoil to obtain the parameter that is the resistivity of the soil. So this measurement can provide a bidimensional data of the subsoil in terms of resistivity. So why resistivity is so important? Because it is connected mainly to the type of soil, but when you are making a monitoring, it's mainly related to water content. So how does it work? So you need the system that is a georesistive emitter, you need cables and electrodes. This system can inject current, measure the voltage, and obtain thanks to the second law of Ohm, the resistivity. You have really a lot of pros with this measurement because, as I told you, it's a good proxy of water content, and it is a bidimensional data, so it's not only one point data, and you can obtain a result over larger section of soil, hundreds of meters, and you don't need to core in the dam. While you perform manual measurements, that is the measurements that have been performed so far, so with a portable instrument, you can have also some cons because for sure it's a quite complex field work while you are making measurements in the field, and also you can have some ambiguities in the solution because you one picture of the subsoil, and you cannot understand really well if your value is related, for example, to the soil composition or to the water content. And also you need an external software to process the data, and it's not so easy sometimes. And if you want to repeat the measurement, can be quite challenging. So for that, I will speak about automatic ERT monitoring. So it's a new application of an old technology, and you have a system that can perform automatically measurements a long time. So you can overcome some of the main cons of manual measurements. So speaking about the complex field work, obviously it's a fixed system. So you install the system once and then you don't need to go on the field again. Speaking about the ambiguity on the solution, obviously we are speaking about the monitoring over time. So you are interested in see the changes in the parameter. And you don't need to process the data yourself with an external software, because in this case, there is a platform with an automatic inversion of the data that is an important procedure to obtain the real data. And also, there is no issue in repeating the measurements. It's totally automated, and so you will have multiple measurements per week. So what can you do with this tool? You can follow over time the processes underground, and so you can keep track of different processes before it's too late. This system, the Greta system, geological resistivity for time-lapse analysis, is designed by Alessai Lastem with the Politecnico di Milano. It is a system composed of hardware with the georesistivity inside the box, two long cables and electrodes that can be put in a small trench to inject the current. Then there is the software part, because the system is communicating with a cloud platform, and so you can easily control the data and also program the system remotely. The system can be also integrated with other devices. So, for example, rain gauges or piezometer, and also the platform allows you to analyze the data, export the data, and also integrate through APIs in other platforms. So, speaking about this particular application of TSF, what this system can add to more traditional technology, you can follow over time, for example, the seepages, and also spot concentrated seepages or under seepages. And really important, you can analyze the saturation of the dam, and also have information where some parts of the dam are not fully saturated. So you can have information about partially saturated soil, and you can follow the watering process. You will see later on an example, and see where the groundwater level is. So all these processes are key factors in TSF stability. It's a really practical presentation. I want to focus on some case studies that we have in dams. I have here some example in a copper mine in Chile, gold mine in South Africa, bauxite mine in Australia, and the platinum mine in South Africa. This is the case in South Africa, the gold mine. The The objective was the control of the seepage and saturation in the TSF wall, and the installation was done on the crest of the dam. Here you can see the different steps to perform the installation. That is really easy. So the step 0 is the configuration of the router. Since the system is connected to the internet, you need a local SIM card. Then the step 1 is the excavation of the trench. In this picture, you see a really big trench because the machinery available inside was really big, but the trench can be really smaller. And the plinth and pole installation, then the mounting of the main station, the position of the cables, the 2 cables with in total 48 electrodes. You can see here the picture of the electrodes are stainless steel plate electrodes. You can vary the distance between them, so you can obtain a longer profile and also a deeper profile. In this case, the profile is 141 meter long and 22.5 meter deep. Then you close the trench and immediately the system is online. You can control the data through the cloud platform. This is an example of some data in this dam. This is the typical section obtained from resistivity measurement. So here you see these values are resistivity. Where you see blue is lower resistivity, so higher water content, and where you see red is higher resistivity, so lower water content. There is an inverse function between the 2 variables. This is a measurement before rain, and this is a measurement after some period of rain. You can see that the situation is quite homogeneous on the dam, but you have this part below that is where the groundwater level is. You see this lower resistivity. After these two measurements, this is the percentage variation after rainfall. You can see the infiltration of the rain with this blue value that is decreasing of resistivity. So you can spot exactly where the rainfall is infiltrating in the dam. You can also perform some time-lapse analysis. So in this case, it's the average value of the first 4 meters of the facility. And you can see the evolution over time. Unfortunately, in this dam, they don't have a rain gauge, but this variation is due to the wet period. And so you can see that the dam is getting wet and wetter over time. And all these spikes are connected to rainfall events. This is another case, the bauxite mine in Australia. As I told you, it is a dewatering project. So here you can see an adapted size of the trench is really small, and all the process of installation is always standard, always the same. So the objective is analyzing the evolution of saturation over time after the capping of the facility. Here you can see one of the results. All this blue part is fully saturated. So below 4 meters, all the embankment is fully saturated. And inside, outside, there was also a pre-existing piezometer that we could integrate. So in the cloud platform, you see the resistivity section and also the position of the piezometer and the position of the groundwater. So the 2 data are really consistent, and we could integrate all the data through APIs in real time in the platform. This is another time lapse of 1 year of monitoring, and you can see this is the average resistivity of the first 4 meters that are the partially saturated one. And you can see that during dry period, the resistivity is increasing. Then there is a quite stable period, and during the wet period, here you can see also the rainfall. The resistivity is dropping down and is going up after the end of rainfall. So you can appreciate with this analysis how the facility, this part of the unsaturated part, is getting drier after 1 year. So the client can have a number indicating that the watering process is good. This other site is in South Africa. The objective was always the analysis of the saturation and seepage. Here, this is the resistivity section. It's another way of visualize the data with contour plots. You can see a really stratified situation. The blue part is fully saturated. The surface is quite dry. It was a really dry period, while you can appreciate the variation between the saturated part and the dry part, and it is all this unsaturated part. So you can have an estimation of the water content. If the soil is really homogeneous, you can convert the resistivity into a proxy, obviously a proxy of the water content of the soil. Here you can also appreciate that there is a non-homogeneous part with more water. In this site, they don't have a piezometer, but it's really clear that these really low values are connected to saturated part. And thanks to the platform, you can also make this time-lapse graph. So, for example, I've selected the surface, and you can see that during this period of analysis, the soil is getting drier. So you have the average, minimum, maximum value over time of the average of this part. While this is the partially saturated part, and you see that it's quite constant, it's really important to see that it's not decreasing, because if it's decreasing, it means that it's wetter. So in conclusion, geoelectrical measurement can add really value to the information related to the dam about saturation, groundwater level, and concentrated seepages. And the automation of this process is really beneficial, because you can keep track of all the processes over time. For example, we used to have one measurement per day, so you can really the evolution over time. The Greta system is off-the-shelf solution, and it's really beneficial for this monitoring of hydrogeological resiliency itself. Thank you.
Thank you very much, Greta. Then I think we have something online then. We go on the chart. We'll do questions at the end after all the presentations. So just save the questions until the end of the session.
Check on Hita Heroes.
Yeah. So Simon, are you with us online?
Simon, but you guys.
Okay, then we'll go to chart. Okay, so Chart he works at the Institute of Mine Seismology, IMS, where he works with time-lapse monitoring and seismic interferometry. So Chart, you're with us online?
Yes, I am. Can you hear me?
Yep.
You can share your screen. Okay.
Can you see my screen?
Yeah, we're all good.
Okay. Good morning, everybody. My name is Chartevit, and I'm head of the Applied Geophysics Department at the Institute of Mine Seismology, or IMS. And today I'm just going to take you through a journey over the last decade in applying seismic interferometry and ambient noise tomography on tailings storage facilities. So just briefly, IMS is the world's largest private research organization focused on seismology in the mining industry. We develop methodologies and technologies, services to monitor, image, and model the subsurface related to mining. In the early 90s, we began this company monitoring the deep gold mines of South Africa, and now we have nearly 400 real-time seismic monitoring systems around the world in both underground mines, open pit mines, and tailing storage facilities in about 39 countries. So first off, what is seismic interferometry and what is seismic noise? Well, many of you may not be familiar with seismic noise, but you may be familiar with something like the signal shown in the red box on the right, and that's a small little earthquake, a tiny little one that occurred in a mine. There's some drilling signal shown on the left, but the middle shows what we would call background seismic noise or ambient noise. And previously, this was just discarded. And this represented a huge amount of data that we just simply threw away. And it turns out there's a real treasure trove of information in there if you're able to access it. Note also that these are tiny vibrations. You know, the small little earthquake, magnitude -3 earthquake here, had vibrations of 10 to the -5 meters per second. And the ambient noise is even smaller at 10 to the -7. What are some of the sources of seismic noise? Well, the major source around the world is from oceans. As waves interact with the continental coast, they impart a pressure wave onto the ocean floor. And this is pretty much recorded everywhere on the planet. But the other major source of seismic noise comes from anthropogenic activities. So as we drive our cars, use machinery, we all contribute to the ambient seismic noise. And this is shown fantastically in this study that was done during COVID-19, when many of the cities around the world went into lockdown. We could see very accurately when they did this by looking at the ambient seismic noise. And this was what is now known as the global quietening. Basically, this is shown by the white line in the figure on the right. That's the period after which all these cities around the world went into lockdown, and ambient seismic noise went really, really low, and highlighting how much of a contribution humans make to these, to ambient seismic noise. So this is first thought about in the 60s by John Clairvaux, and the main central tenet to this is we use these ambient noise, which just looks like wavy nothing signals, but when we cross correlate them, we use a mathematical operation of cross correlation. This correlation can tell us something about the medium in which these waves have traveled through. This is generally used in kind of two applications. I'll run you through how we're using each of them in tailing storage facilities. The first being using the direct arrival of these cross correlations, and those are generally for imaging, the direct speed at which a wave travels in the subsurface, and then the scattered coda for time-lapse monitoring. So how do we measure velocity changes? Well, here's a cartoon to try and explain it. At some point in time, we calculate the cross correlation, and this can represent how a wave has multiply scattered through the subsurface from a sensor A to sensor B. Now imagine at some later time the subsurface has been weakened. Either it's in a hard rock setting, it's been fractured, or stresses have increased or changed, or fluid saturation has changed, and now in this case, we're representing it by fractures forming. This path, the wave that traveled along this path, now takes slightly longer. And if we compare the cross correlation at this previous time to the current one, we can measure very tiny changes in how fast these waves travel. And it's this that tells us what's happening in the subsurface. We generally, for time-lapse monitoring, use the coda portion, which is these multiply scattered waves, not the wave that just went directly from sensor A to B. This is kind of a little animation that tries to explain how we measure this. We use tiny windows in these cross correlations and look at these shifts, and that represents a change in the velocity in the subsurface. Generally, this is related to the shear wave velocity. So when we talk about a change of velocity, I'm mostly referring to a change in shear wave velocity. Why do we use these scattered waves? Well, the point is they have spent a lot of time bouncing around the subsurface, sampling it. And so they sample the whole medium. The bottom figure shows an example of modeling of this. And as time goes by, you can see that what starts out as a wavefront becomes this scattered, diffuse waves. And it's these that we are using for this type of monitoring. So where's this been applied? This is actually nothing that IMS has developed. This has been in the last 2 decades. This has been used in academic settings to monitor the rock response to earthquakes, monitor volcanoes, landslide failures, and in recent years we've contributed into monitoring earthen embankments and tailings storage facilities. And I'm going to take you through a little bit of a journey through how we got there and how we're using this. And then I'm going to transition over to how we're using this to image the subsurface. So here's ambient noise monitoring. Here's just some examples of how this is being used. The most famous example is, in this case, showing how, following the Parkfield earthquake in the US, we can see how seismic velocity decreased as the ground shaking from this earthquake damaged the subsurface, and then how over several years it slowly recovers. Here's examples, and these were the first sort of studies that grabbed our attention. This is from 2008, where researchers were able to detect decreases in seismic velocity, shown in red in the curve on the left, that preceded periods of volcanic eruption, shown in green. And they even started to, they titled this talk "Towards Forecasting Volcanic Eruptions." So really sort of showing, hey, this is a tool that we can monitor changes in the subsurface prior to something and forecasting a volcanic eruption. But it was this study in 2012 that really grabbed our attention. This is from the Swiss Alps, and there was a well-known landslide. They had a good understanding of the local geology and had done a electroresistivity tomography across the landslide. And on either side of the landslide, they installed 2 seismic sensors. And again, they found a dramatic early change in the subsurface velocities prior to this landslide failing. Even pushing them to title their publication "Ambient Seismic Noise Monitoring of a Clay Landslide Towards Failure Prediction." And that was pretty groundbreaking. Here were their results. About 20 days prior to this landslide failing, they detected about a 2% decrease in shear wave velocity. And in the several days before the landslide, shown as this gray band here, they detected up to 7% decrease in velocities. The researchers at the time attributed this to the weakening of the landslide interface between the landslide and the bedrock below, it being lubricated by sort of the rainfall that led up to this particular landslide failing. So in 2012, this really grabbed our attention at IMS, and we thought, hey, this could be something that we could use in other applications to monitor potential future failures. And the final study that sort of really pointed us towards dams was this one from 2016, done at Colorado School of Mines, where they installed seismic sensors along the crest of a laboratory embankment, and they induced a failure, sort of piping failure, in the middle of the dam. You can see it in this photograph here. And what they were able to show is, if you use different pairs of sensors, so for example 1 and 3, these two, you detect almost no change due to this. But for pairs that are close to it, for example 4 and 6, you can detect up to 20% decrease in seismic velocities. So what this again showed us is, if you have an array of sensors, you can not just detect early onset of maybe something happening in the subsurface, but that it could you could also say where, and so some kind of understanding of where these changes are occurring. And it was about this time that we obviously we sort of were struck by some of the failures of tailing facilities, most notably at the time Samarco in Brazil, and that pointed us to, hey, this could be a perfect application for this kind of technology. But this wasn't the only case. There have been several failures. Mount Polly in Canada in 2014, Kedia East in 2018, and Brumadinho in 2019. This showed us that this is happening, and even in many of these cases, these facilities were well instrumented with other geophysical equipment, and so maybe there was room for additional monitoring that could help understand why or potentially prevent some of these future failures. So in 2017, we turned to a tailings facility in Tasmania, in Australia, and we tested and trialed this technology. This is a facility called Princes Creek, part of Mount Lyell mine, and we deployed 10 seismic sensors and monitored velocity changes over a period of about 25 to 30 days. During this time, we were extremely lucky. There was huge amounts of rainfall, about 400 mils of rain fell, and there were several areas shown in these red boxes where there was vegetation growth because of consistent seepage, and also a seepage that was monitored during this period of heavy rain. And here were our results when there was several major rainfall events. The lake level of the facility rose by nearly a meter, and this really sort of pressured fluid to seep through some of these pathways, and we were able to detect several pairs of sensors that detected a 2% decrease in seismic velocity that coincided with the region where there was significant seepage visually observed. So we're observing this change in fluid, in this case seepage, through these well-known pathways. In fact, in this case, it's actually this contact with this sort of local topography that really that drove this seepage. We were able to detect that through seismic interferometry, and we published these findings in 2017, and subsequent to that, we have generated specific hardware at IMS that is dedicated to being utilized on tailing storage facilities. But also that this kind of monitoring also monitors ground vibrations. And if you want to sort of make sure that your facility is not being exceeding vibrations from, for example, as specified in your seismic hazard assessment of a particular structure, you also get that kind of information from these sensors. So you're getting both changes in the subsurface from interferometry, but also measuring vibrations to ensure you're meeting the design criteria of your facility. So now, 8 years later, we monitor over 40 tailings facilities in Brazil, Mexico, USA, Australia, New Zealand, Indonesia, and Finland, with many more starting to turn to seismic monitoring to understand both vibrations and changes in velocity in the subsurface. I'm going to pivot just for my last little bit here into passive seismic imaging too, because the same technology can be used to measure. 2 minutes. So the same technology can be used to image the subsurface instead of just measuring time-lapse changes. This has been done in various applications, from continental crust of Australia to the caldera of volcanoes, and it's mostly been driven by this boomless technology of these portable seismic devices. Thanks to the oil and gas industry, have come rapidly down in cost, and we're able to deploy dense arrays of them. So we deploy anywhere from 10 to 1,000 of these in arrays, record seismic vibrations for up to 30 days, and we utilize the dispersive nature of surface waves to understand what's happening in the subsurface. In most cases, we're using Rayleigh waves because they have a vertical component, and Rayleigh waves in general have sensitivity to the subsurface at different frequencies. So by recording different frequencies, we can essentially determine what is the velocity up to 2 kilometers deep. And we applied this in a mineral exploration prospect application initially, where we deploy these dense arrays to try and image for new potential mineral deposits. But we suddenly realized that this can also be applied in various applications on much smaller scales, including geotechnical applications. We applied a study in 2018, which we also published, on a tailings facility in Welkom in South Africa, and we were able to detect a plume of low velocity shown in this result in the bottom here that extended to surface exactly where we were able to observe visual seepage and vegetation growth at surface. We followed this up. This was just a 2D study, but we followed this up with several 3D studies where we deploy them in dense networks and able to image complex 3D structures of fluid seepage in the subsurface through these arrays. And I'll fly through this example here, where we're sort of just various cross sections through the 3D model of the subsurface that we can produce from ambient noise tomography. So let me conclude. Basically, this journey has shown us that seismic interferometry really offers a cost-effective and real-time solution to monitoring internal changes in tailings dams, with the key potential to provide crucial early warning of future failures. Also, ambient noise tomography presents a non-invasive and environmentally friendly technique. We don't need active sources and hammer shots, etc. And this allows us this technique to image the internal structure of tailings storage facilities. So here's some of my references, and I'm happy to take questions later on. Thank you very much.
Thank you very much, Charles.
Yes, Simon's here.
Yes, Simon's here.
Yes.
Okay, so Simon, are you ready to go?
Yes. Can you hear me?
Yeah, we can hear you fine. So next speaker is Simon from Elexon Mining that will talk about smart markers.
Can you see my screen?
Yeah. Yes, all good.
Yeah, excellent. Well, good morning, everyone. I will talk about the wireless in-ground monitoring system. So it's probably a bit different to the previous presentation, as we work with in-ground sensors. A bit of a background on where we are coming from. So Elexon Mining has its origin in underground cave mining, so block caving, sub-level caving. And we've developed technologies that are now widely used in these mines all over the world. So we have wireless technology for monitoring material flow in block caving, and which is called Cave Tracker. And the other technology that was developed for cave mine is called GeoForesight, which is a wireless in-ground monitoring system with sensors. And this is the technology that I want to talk about here. And we're applying this technology that we're using in cave mining in other areas, such as open pit and tailings dams. And the reason being that this wireless in-ground technology is complementary to other monitoring technologies, such as cabled, and I believe they have been talked about in other presentations. Now they are complementary because there are certain applications in mining where cabled in-ground systems are challenging to install and to use, or even impossible. Being cables can get damaged. When they get damaged, they will not, the sensing system will not work anymore, or they are not possible to be installed in the region of interest. And this is why we believe this technology is complementary to the existing alternative monitoring systems. Now, there are certain areas in tailings dams that are hard to instrument with in-ground or subsurface monitoring systems, such as in the foundations or in the tailings material itself. And as tailings dams grow and with lifts get increased capacity, they typically means that instrumentation needs to be reinstalled or spliced together to cover the existing instrumentation, but also when new instrumentation gets installed on top. So the advantage is that wireless in-ground, which is different to the wireless data logger. So it's actually the sensors that we provide are battery powered and without cables attached and communicate through the ground. Is the advantages are that we can reach areas that are hard to reach with cabled instrumentation, that are hard to maintain with additional lifts of embankments, and where multiple sensors together in one location need to be used, and also in high density. So how does the system work? So what the system provides is a mesh network. So each of these devices, here's an example, is operating independently with battery power and radio communication. And what we do is we install them at approximately 2 meter distance in the ground, being through drilling holes and lowering the devices down the hole or laying them out in a trench at these distances. And the communication starts at a data logger, and then hops along the chain of devices installed in the ground. And each of these devices has sensors on board, and these sensors can be measuring tilt and or pore pressure. So we have a variant that measures tilt only, and the variant that measures tilt and pore pressure together, so that each of the sensors has these capabilities. And what we measure with this is we're looking at angular distortion as an indicator for inferring strain or movement, and ground deformation and pore pressure. The tilt has a sensitivity of plus minus 0.002 degrees. It's quite a sensitive device. And it also includes the azimuth direction of the change in tilt. And the pore pressure is plus minus 0.125% of its range. And additionally to this, we can measure temperature at the location of each of these devices. Now, what's the way we can install them in a tailings dam? In this case, we'll put an upstream tailings dam. We can drill holes from the surface down into the structure and through tailings. There are also other ways to install, like if during the construction we can lay them out and cover them, or we can install them under before construction into the foundation. And the concept is that we have, again, these mesh networks of sensors that communicate with each other. And what we can do is we can create three-dimensional structures. So we can extend these arrays of sensors in various directions, and they will continue to communicate with each other and out. And the advantage is if we have any displacement in the ground or disturbances on surface, then the cable is like there's no cable to get damaged, and the system continues to operate. And again, in the cross section, a sketch of an installation, we can install them through an embankment structure, through into the tailings, or into the foundation, either through drilling or pre-construction. And this allows us to see any changes in the tailings deposition or in the embankment structure. This is an example of the data that we capture. So what we have is we have, on one hand, a change of tilt of each of the devices installed. So at each location, we will see if there's any deformation, disturbance of the ground and the magnitude of it, and this over time. And we will also see the azimuth of this change of tilt. So in which direction do we see this angular distortion? We resolve this for each of the sensors in the ground. So what does this give us? Sorry, there's an example of pore pressure as well. So we have the variance that measure pore pressure. And this is an example of an installation in a tailings dam where we see the measured pressure and changes over time. And it correlates well with traditional vibrating wire piezometers we verified in various mine trials. So we can compare that directly. So the applications for this wireless technology is where it complements traditional instrumentation, where we need a high density of tilt and pore pressure measurements together in the location, so we can have as a high number of these sensors, and we're not restricted by cables. Whereas if we want to install a large number of cable sensors, we will end up with big bundles of cable that are potentially get damaged. We can create three-dimensional arrays of sensors that are linked together. These arrays can be extended. So if we build up the embankment, we can just add on to the existing array, and the system continues to operate, including with the previous sensor array. It can reach areas that would be challenging with cables. Cables need to be heavily protected, or due to the construction sequence cannot be deployed, or where surface disturbance by heavy machinery would damage cable. So this is complementary to traditional technology and enables further monitoring of extremely challenging areas. So this is an example of an installation in a tailings dam. These were holes that were drilled through the embankment, and there's some example of pore pressure data, so where you see the deposition of tailings. So these sensors were installed during the construction, and over time this TSF will be filled with tailings material, and these are still dry, but what we're seeing is a deposition cycle of tailings measured by one of the sensors. We have another example. This is a trial that we're running together with Ground Probe at the Kawe tailings dam, where the the geophotovoltaic sensors were deployed into tailings material. So this was an array there was a trench dug across the surface, complemented with holes drilled vertically to measure pore pressure and tilt. And after that, there were dry stack deposition. And we continued monitoring this array, even though heavy machinery was driving across the surface, and the response of the sensors was representing the machinery and the deposition rail. The installation of the devices typically can be done through drill holes. So we use installations through the inside of the drill string using a fiberglass rod that we attach the sensors to. We load them down and then grout the hole and remove the drill string. Alternatively, we can dig trenches and lay the sensors out and then backfill. This is a possibility that during the construction of embankment can be done so that no drilling is required. And we can extend. Yeah.
Sorry, you have 2 minutes.
Okay. Yep. So these arrays can be extended, so in 3D, as I mentioned before. So we have drill holes. We can lay out markers on surface that connect drill holes all the way to a data logger, and we're pretty flexible when it comes to these shapes, as long as we have the sensors within 2 meters of each other. And that concludes the brief introduction of the technology. And of course, I'm happy to discuss any further ideas and feedback on this presentation and technology. Thank you very much.
Thank you very much, Simon, and thank you very much for staying on time. I wasn't sure how many more slides you had.
No, it's
we will save the questions for Q&A.
sorry.
Yeah, go ahead.
I just want to thank everyone for organizing this workshop. I know it's a lot of effort, so I really appreciate that. Thank you very much.
Thank you. Next presenter is Alistair Belson from Tre Altamira. He will be talking about dam and slope instability monitoring using INSAR.
Morning, everybody. Morning. Just goes forwards back here. Right. Good morning, everybody. Hello. My name is Alistair Belson. I am the area Asia manager for Tre Altamira. I apologize. I've picked up a bit of a cold, so I'm trying to hold myself together with mints and coffee. So apologies for that. For those of you who are not familiar with INSAR, it means interferometric synthetic aperture radar. We have been put into the emerging technologies session for this seminar, but in actual fact, INSAR is a well-established technology. Like my fellow presenter, Greta here, we're actually a spin-off from the Polytechnic University of Milan, founded over 25 years ago. And we are the inventors of the technology, and over the last 25 years, we've grown to be the world's largest INSAR company. Unlike my fellow presenter Greta, I didn't manage to name the technology after my name. It's actually Alistair Sar, I guess, was just a bit too much of a mouthful. But to make it short, because probably some of you will have heard about INSAR, some of you won't. But today's presentation is really just about how does the technology work basically, and then the application. So it means interferometric synthetic aperture radar. So we're using radar sensors on board satellites, which are circumnavigating the globe all the time. And these satellites have been launched since 1992. So effectively speaking, we cover the entire globe almost every day, not necessarily with the same satellite, but on once or twice a week or every 2 weeks, we get data over a certain area. So these data sets have built up over now decades, and we can go and take that data and then process it either back in time or forward monitoring. Okay. Like I mentioned, we've been around for 25 years. So really, INSAR is a well-established technology in monitoring ground movement, not just on tailings dams, but also on civil dams and any ground movement anywhere in the world. So there is a difference between the satellite data that's available and the processed results, which would be the INSAR results, which I've shown here an example image. Our goal is to process the satellite data to give a very dense map of information of ground movement throughout the period of the satellite data that we've processed. So if this is a 5-year map, for example, I'm showing areas in red, which show areas of movement throughout that 5-year period. Unlike, I guess, some of the other presentations from today, it's important to stress that we're using a satellite that is 800 kilometers above the surface. And so we are a completely remote technology. We don't need anything installed on the ground. Of course, we have limitations, and I will cover that in all fairness at the end of the slide, but we don't have anything installed on the ground, which means we don't have any people to go in and maintain the sensors, and we don't need to maintain the sensors on the ground. But the goal here is when we're monitoring a dam, and the application here for let's say tailings dams or civil dams is we're monitoring on a regular basis such that every time we get a new satellite acquisition over the dam, we process the data, we update the time series of movement, and then we show you how it's moved with respect to the previous image. How does this help? If there is an instability, a change in trend in the stability of the dam, then we're going to identify, or at least the goal is to identify as early as possible any displacements that might become potentially critical in the future. Okay, so of course we can all shut the door after the horse has bolted and do an analysis once there has been a failure and show what you would have seen, but the goal is to get this technology implemented over dams on a regular basis to map them from a distance remotely and identify those potential failures before they fail. So I won't go into all the details about how INSAR is really processed, but we have the satellites at 800 kilometers above the surface. I can tell you that we can see millimeters of movement on the ground. There might be some questions saying, how do you do that? It's really well published in the publications and the papers. The physics and the maths show it very clearly. You can see these millimeter changes on the ground, even with a satellite that is 800 kilometers above the surface. They have fairly wide areas, which means that we can go down to really very small areas, perhaps like a meter square, or entire regions. So if you're looking for landslides, we can process very, very wide areas, including, for example, entire mountain ranges or entire countries. And now we're processing, in fact, an entire continent of Europe in one analysis, or we can come down to the single dam. Over the last 25 years, like I said, TRE were the founders back in 1999, and we have improved our processing capacity over the last 25 years, but so also has the satellite element. So as the first satellites were launched in 1990, over the last 2.5 decades, we've got more and more satellites, which gives us more and more processing data capacity, as well as in the different bands. And again, I won't go into the details of the different bands, but certain bands have different applications for different projects. The amount of data that we can acquire now has significantly increased, which allows us to process, let's say, for specific projects. So in this case here, I've just chosen an area in India. I believe it was Odisha, but it might also be New Delhi. The tracks in blue show what satellite data has been available over the last few years. So going back in time is also a possibility with this technology. Right, so how do we measure the movement? Very simplistically, if we're sitting in this building or if we're looking to monitor a dam, the satellite at time one would collect an acquisition, so take a satellite image. The image is basically useless unless you process it with a robust INSAR processing chain. If this building moves or the dam shifts or there's an instability, for the specific area that is reflecting on the ground, and theoretically there'd be lots of reflections over a dam face or over this building, for example. If it shifts through time, when the satellite passes again, it takes a second distance, satellite down to ground and then back again. So it's a two-way travel time. And then we calculate the shift in what we call phase. And that's where we get our millimeter precision data. not all these satellites, the L-band, for example, won't necessarily give you 1 millimeter of accuracy, more in the range of 5 to 10 millimeters. It's more suitable for landslide mapping, whereas the higher resolution C and X will give you the millimeter precision. So that's enough on how the technology works. What about the application? Here is a landslide on a reservoir slope. Here's a dam down here. The focus of this analysis was not the dam itself, it was the reservoir slopes around the site. Of course, if a landslide fails into the reservoir, then we have the potential issue of the overtopping with the water, right? So this is one of our major applications for INSAR in monitoring the landslides. Perhaps you have in situ instrumentation, perhaps you don't. This satellite here is in fact that L-band that I spoke of before, which is particularly suitable for landslide mapping because vegetation is, in some cases, a limitation of INSAR. The higher resolution bands cannot penetrate through the vegetation, whereas the L-band, which is a longer wavelength, can penetrate down to the ground, and so we can see through and then identify the areas in movement. So this would be a standard deliverable of an INSAR product. So we've got a platform, and then we deliver our data set through the platform through a secure login to provide just the data set for the area that each project requires. So if it's a dam, then we just upload the dam data. There are various tools on the platform which allow you to interrogate the data, but essentially speaking, we're showing how the ground has moved through that period of time. So for this specific analysis, it was a 2.5-year data set, which over that period shows an 82 millimeter displacement for that area in the landslide. Quite what that means in terms of risk is not for us to determine. We would leave that to the geotechnical engineers, the geologists, to then interpret that data. So really, INSAR companies are instrumentation companies. Yeah? But each of these measurement points, of which there are millions in this particular example, and I'll show you some more as well, has a time series of movement. And every single satellite image that's acquired through time is another point on the time series. So as we go forward in time, if I'm actively monitoring that satellite, that landslide, I'm adding another measurement point to the time series, and then we're looking to capture if there's any change in behavior through that period. So for the applications for this seminar, and indeed the longer conference where we'll have a booth, will be civil dam structures, mining TSFs, and indeed all slopes in mines, and then of course reservoir slopes. This example came up before. Some of you will be familiar with it, the Cadia mine. This was an example of, after failure, we went back in time to see what would have happened with the INSAR data before the failure. We normally color code our points of movement as being red. As you can see, that we don't get measurement points over the area where there's wet tailings. That's a limitation of INSAR. It could be due to two factors. One, there's water, or two, there's a lot of ground change, as in lots of new material. So if you imagine a prism, an in situ prism, if you add more material on top of the prism, you'll lose the prism. So you have to move the prism and then put it back on the new surface of ground, at which point you'll start again measuring its displacement through time. The same is true for INSAR. Remember, we don't have anything on the ground, but when we see those changes, we lose what we call the coherence, and so we lose the point for that period of time when the ground has changed. So this is exactly what we're looking to provide, really, is if they had been monitoring with the INSAR, then they would have seen this acceleration. We see a compaction or a ground movement for the first period, stability, which is this flat area here, and then several months prior to the failure, we see it start to accelerate. And that's really the key scope of an INSAR analysis over a dam, is to capture those displacements before the failure. And here's the measurement points across the failure area. That's the direction in which it failed. And you can perform an inverse analysis with time to failure prediction if required. And that shows basically that the time to failure agreed pretty well with the actual date of the failure, looking at the acceleration in velocity here. So really, we're identifying those accelerations through time. Certainly with the mining companies and the TSF monitoring groups that we work with, they're looking at this data set on a very regular basis. The goal being, I know where I've worked on my mine, I know where my theoretical instabilities are, and so when I'm looking at this map and I'm seeing a movement, I can then relate to what I've done on the mine and say, I'm okay with that. That movement makes sense. The question is, when I see a movement that doesn't make any sense, what do we do about it? And again, we're an instrumentation company, so we collaborate, and then we help understand the INSAR data, but the INSAR data itself needs to be interpreted by the geotechnical engineers. Here's a cross section through time, the same data that I showed you. As time moves forward, the displacement is then mapped on the x-axis down here. We see really quite some strong differential displacement across that area where it failed, pretty much well in advance of when it actually failed. The second example here is of a slope. So I've integrated here two data sets. One is ground radar and one is our satellite measurement points. Our individual points that you can see here are the INSAR points, and then the solid color is the ground radar. INSAR is not a real-time instrument. So if you have an instantaneous failure, INSAR will not be able to help you. We're looking for the long-term slow displacements that perhaps aren't detected by the in-situ instruments. We're not also in competition with these in-situ instruments, right? We're very complementary as a data set, as will be shown by this example here. This area here failed. The ground radar almost clipped the edge of the area that actually eventually failed, which is the red outline here. What is interesting is that the timescale to failure between what the INSAR saw and then what the ground radar saw, they show very similar displacements, but the time periods are really quite different. So ground radar has its limitations, just like INSAR does. And one of the limitations of ground radar is the minimum velocity that they can detect. So we're looking at millimeters per year, and they're more in the range of a few centimeters. So the displacement that they detected was very similar with acceleration 1, 2, 3, about 22 days maximum before the failure. INSAR has seen it already 9 months in advance, right? Simply because of the different velocity rates that we're detecting. I've mentioned before that INSAR is not a competitive technology. That's not our goal to replace in-situ instruments. We see an area on the ground that is reflecting, and you may have a very specific point that you want to be monitoring. We might be seeing an area of the ground that's moving, right? So from that point of view, we're not trying to remove or reduce or outdo ground instrumentation. These graphs here simply show how the data sets agree. Remember that we're looking at perhaps an area of movement on the ground, whereas an instrument would be monitoring a very specific factor. So you may have to also consider the satellite line of sight, which is not perfectly vertical. It's coming down at an angle. We call it the line of sight. And that may not be sensing the exact same movement that your sensor is. So if you're integrating INSAR data with in-situ instrumentation, you need to just bear in mind which angle of the ground, of the looking angle you're looking at to compare it with your in-situ. 2 minutes, sir. Don't worry, I've got 2 minutes left. So we've processed some data over India as a small teaser for this this conference coming up. This is the Tiri Dam area in Uttarakhand. This is the ALOS data set. So this is what we call an L-band. Again, this is really designed to be identifying landslides. One of the first things you'll see is the dam is actually in this area right here, whereas the data covers an enormous area. I believe on the latest count, we had something like 45 million points on this data set, which is also not the full satellite tile that we could process. Immediately, the areas in red and blue pop out. In this case, red and blue mean what is moving in one direction, and the other is, and then the other side is moving down the other side, probably down the flank of a mountain. We only got this data set 2 days ago, so it's fairly fresh for us. But there are some points on the dam itself. This is the highest dam. I think they call it Earth Dam in India. I was unfamiliar with this until yesterday, so we've processed then a second data set over this dam, and again, we've color-coded it according to its movement. So to conclude on this last couple of slides, we color-code the movement. Red is moving down away from the satellite and blue is moving towards, but there's an area of subsidence in the center of the dam there, and if you're interested, please come and find us in booth 51, and I will show you the data set. To be fair, to be complete, there are limitations of satellite INSAR. It's not real time. So if you're expecting a real time instrument, then or a very critical area that requires real time instrumentation, please do install it. INSAR will not be able to identify instantaneous failures. It can struggle with certain satellites over vegetation. We do have a solution for vegetated areas, like I said, accepting the 5 to 10 millimeter accuracy limitation. Where you're rapidly changing the ground, we will lose the coherence for that period. Once you stop changing the ground, the coherence will come back in again. Again, it's similar to the in-situ instruments. And then, of course, where you've got water bodies, we don't get the measurement points. Last slide here, then. For those who haven't considered using INSAR for your dams, your slopes, or your TSFs, I've listed here a few points as to why you might want to think about it. Number one, it's completely remote. So again, no teams on the ground need to install anything, no maintenance, lower risk in some cases. Millimeter displacements, similar to your in situ, as well as vertical and horizontal displacements as well, if you use both satellite tracks. I didn't talk about that much in too much detail, but 2 satellite tracks exist, and so you can process them to create true vertical and horizontal displacements. It's extremely complementary with in situ. Again, we're not competing. Very, very high density of measurement points compared to your in situ instruments. If you have the budget with in situ, great. But if you have a wider coverage with the INSAR, then it'll give you very high density of measurement points. Satellite data covers enormous areas, and so we can cover very wide areas with just one single analysis. And my last point here is that satellites have flown for decades. Most likely over any of your sites, there will be several years worth of data. So if you're interested in going back in time, the last 1 or 2 years, you can see what's changed on the ground and get a current state of play in terms of stability of the mine. Okay, thank you everyone for your attention. Thank you. Thank you, sir.
Thank you very much, Arthur, for an interesting presentation. We're moving straight on to the next. So next is Vijay Chandel, that is going to tell us about the GeoRadar.
Good morning, all. Myself, Vijay Chandel, and yesterday I presented you the methods which is going on, which are the conventional methods like total station GNSS and the scanners to monitor the structural systems. Today, I'm going to talk about the GeoRadar system, which is a relatively new technology, and as my good friend just in last presentation shown you the SAR technology using the satellite images. I am going to tell about the SAR technologies used by the radar system installed in the ground. So I will not talk about the hexagon a lot because yesterday already I have covered this. So today, what are the GeoRadar systems solution used for them? GeoRadar systems are the SAR systems. It is a synthetic aperture radar systems, just opposite to the satellite systems, which data is getting collected by the satellite systems. These are the systems which are installed in the ground and will take the radar data time to time to give you the exact deformation on the dams and within the accuracy. What it does basically, a radar system, if I will talk about a interferometry radar system, it takes images from time to time in every 2 minutes or 4 minutes, and phase shift measurements. It combines the 2 images from the radar and will give you the deformation analysis according to the requirement, according to the threshold you have set it down. So this is just one example I want to show you that first acquisition, the radars, the first phase, it will send one image, send the signals, and it will come back. And on the same time, when it will send back the same image again, and the deformation between the two, it will record that and it give you the results in the accuracy, and which can be helpful for the deformation analysis of the dams. So why? What is the what are the advantages in this system? First is the safety. Basically, when you go to conventional methods, you have to go down to the walls of the dams and install the various prisms or the GNSS system. In this case, you don't have to go there and install something on the face of a dam. You just have to install one system on the other side of the dam. It will continuously doing the monitoring and will give you the results. It is a remote monitoring system. Then it will give you high spatial resolutions with the accuracy. You don't have, you are not required to make the contact or the continuous monitoring for means you don't have to go there again and again to do some analysis, or it will do continuous monitoring according to the requirement as you have set it down. It is having the all weather capability, means any weather will work for that. It doesn't mean that if it is a fog or something, it will not collect the data. As it is a radar technology, it will collect the data. And the best part of this radar systems are that they are on the long range operations. Means you can, starting from the 50.50 meter up to 5 kilometer, you can track down the resolutions on this. So as I just talked about that, there are two kind of systems in this. One is the fixed system, which can do the analysis up for a long range up to 5 kilometer. So this is one system in our portfolio, which is called IBIS FM. So what is it has the range of 4,500 meter, means you can track it down up to 4,500 meter in capability, and having a very broad coverage area. So just you can see in this that how it actually works. Basically, you can see that it moves down one place to another, means the radar head, this is the radar head, yellow is the radar head, and below is the base. So this is a fixed system, means you have to fix it down it somewhere, and you can start working on this, and you can get the analysis done in minutes. So this is the radar system, which you can see that it is moving from side to side, one side to another side, and it is taking the data from time to time, and will give you the results according to your thresholds. Radar stands for radio detection and ranging. So you can see there are two antennas which are basically sending the rays to the radar signals to the particular location and getting back the system. So you can see there are two types of radar system right now. One is real aperture radar and IBIS radar. If I talk about the real aperture radar, it only collects the data to a particular cell. But with IBIS FM, you can get the data from the entire target area gets scanned in one time, and you will get the combined result at one go. So this is the biggest, I can say, the difference between the normal radar and the IBIS radar systems. So you can see the deformation analysis, means the blue one is the, you can see if I will talk about the analysis, the blue one, the actual data should look like, but the deformation is looking like this. So there is some problem. So this kind of analysis can be done very easily using the radar systems. So the best part is that is a 4 kilometer. It is 80° by 60°, the coverage area, the horizontal versus vertical, and it will give you the maximum resolution for the data collection. So this is one example when the final data looks like. So you can see there that if something has happened, that red area where it has indicated that it might be possible in the future, there will be deformation in that side, because maximum deformation is happening in that side, and this can be right now this is for a landslide, but this actually can be done for the dam also. And in India right now we are working with some of the dam on us to install this, and might be we will be able to install some of the solutions right now in India for this kind of solutions. So this is so this whole setup looks like this. This is not only for the ideas I'm talking about. The idea, this is basically the system, various radar companies give. See, this is the radar head, and which also combines with the weather station, and also you can combine with different kind of solutions like inclumeter, piezometers, or all the different sensors which are just installed in a dam, and can get a combined result out of that. And you can also put on the power supply unit with the weather station. Just for an example, we just have installed one system, not in the dam. We have just installed one system in Sikkim for the avalanche monitoring, and it is working with the solar system, and it is giving the result via the satellite communication every day at 3 o'clock, that how much deformation was there in the lake or something. So this kind of system can be installed, and you can't if you are not going there for 7 days or 10 days or 12 days, it will be working on their own with all this methodologies. So this is a very robust system, and so this is just one example. We have installed this system in one of the dam that is in Italy, And this is just one example that how this data look like and how the radar. So you can see here that you can see that how this this is permanently installed there, and you can see the deformation monitoring can be done in how it is getting done. Uh, just for an example, so this is the final graph which you will get after the analysis, and it will generate alarm according to your requirement, according to your threshold. Like you are just saying the showing the red line which is going up, so it will generate alarm for you that this displacement is very high and you have to look for that. Okay, this what I show you is the system which is getting fixed there, and we have the system. There is another system which you don't have to fix there. You can be mobile with that. So this is one system that is called Hydra G, which you can take with you like a total station, and you can take it to different places at different time and do the analysis. Just the difference will be that the range will be little bit low from the long range system. So it is only 800 meter or up to 1 kilometer. It will work. It is same. The system is same. The radar principles are same. Just the thing is that it is very compatible, and you can take it and you can just put in a box and take it anywhere. It will be only 30 kg. As compared to the other system there, which is 70 to 80 kg. So this basically is a mobile system which you can take it with you and do various kind of analysis in slopes or dam or tunnel or building. So this kind of system can be used and for the deformation monitoring on the dam for the mobile applications. And we have our softwares. We have not only us, a lot of companies are giving software which are web based, which are where you can use this kind of softwares in the back office or just say in your control center, and you can get the results on your mobile systems or in your laptop systems and the workflow will be same as it was with the conventional system. All the data gets collected in one go, and it will combine the data. The software will combine the data and will give you the final analysis on your the report on the laptop, as well as it can create the alarms for you and will generate messages, alert, and SMS to give you the prior information of the incident. So thank you so much. If you have any questions.
Thank you very much to all the presenters. So we have some time for questions. So can I invite all the speakers to come up on stage, answer the questions? We also have and we also have Chart and Simon on Teams. So feel free to ask questions as well. Anybody with the first questions? I think there were some questions early on here.
Yeah, good morning. Myself, Kara. I have a couple of queries related to you presented. First of all, my appreciation to you. It was a nice learning lesson for us also. So I'm raising query with related to our operations. Does it have any restriction with respect to the height of the dike? Does it have any restriction? Means it is applicable for any height of the dike, or it is limited to certain heights?
Thank you for the question. Just a clarification. If the technology has some restriction related to the height.
Yeah, what height?
Okay. Yeah, because you have the system with these 48 electrodes. So it's a fixed number, and you can change the distance between the electrodes. The distance between the electrodes is related to the depth that you can measure. So, for example, in the example that I shown before, we had 3 meters between the electrodes, and the maximum depth was 22.5 meters. In some cases, you can reach also more depth, increasing the distance. So in some favorable condition, you can reach up to 40 meters depth. If you have a high facility, you can put more systems. So, for example, on the press, on the peak, and on the slope, and you can have multiple sections that you can control in the same platform.
Yeah, thank you. One more question. Is it applicable for all kind of construction of the dams, whether it is a urban dike or it's a rockfill dike? Because there are some dikes are made by the core, this rockfill dams. So does it have any disadvantage or it will cover?
The important thing for the installation is that the electrodes have a good coupling with the soil, the surrounding soil. So if you have, for example, a dam made of clay or any material that has a small diameter of particles, for sure the electrodes can work really well because they have good coupling and can inject the current really well. If you have more coarse material, probably it's better to put around the electrodes some bentonite or some soft soil to guarantee the coupling, because it's a really important point to obtain quality measurements.
Myself, Vinod Kumar More. I'm from NTPC. We are dike owners actually. So we want to know, the question is from Geo4 side. This, what is the power requirement and what other infrastructure is required for geosensors? Like when geosensor is being installed inside the dike body or dam body, how this sensor will be functioning without power, or any Wi-Fi support required?
That question was for Simon, right?
Yes.
Yeah, Simon, care to answer? I think Simon has left us, actually. He's no longer on Teams. Okay, we can send in the question up.
My other question is from GeoRadar. What is the cost and what skill is required to operate this in the field?
Regarding the cost, we can talk it later because the cost varies from lakhs to crores, depending on the requirement. Basically, the main issue with the GeoRadar data is the communication part. So that communication part we have to look after for the costing, basically how much, and other thing is the electricity and the power requirement. If their power requirement is already there, or you have to require the whole cell. So all this depends, but the costing can varies around 80 lakhs to 5 to 6 crores.
Skill, what kind of skill required?
Basically, there, for running the radar, there is no particular skill required, but for the resolution and the for the study of the data, yeah, there will be some skill required. You have to understand that what are the displacement and what kind of displacement are applicable, and all these things are required. But for running the radar, there is no such skill set is required to do that. It's just a small machine, you can just learn and do that. Normal person.
One question related to Madam, a nice presentation. You had mentioned
One slide wherein due to precipitation there was 25% variation in the resistivity. Is there any correlations you have tried to establish between the resistivity, water content, and the water table variation?
Yeah.
Because these are the nutshell parameters for a geotechnical engineer to assess the understand the stability of that. Thank you.
Yes, for sure. Resistivity is related to water content of the soil, so it's related to rainfall. And obviously, looking at percentage variation, is good to know what is the variation, the percentage variation in the standard situation. So if you have 5% variation, right? You need to control which is the mean variation of your data in stable situation, and then you can.
I think you were relating it to the presentation, the 25% is change of.
Yes, yes.
Okay, sorry, I didn't understand. In this case, the 25% variation was related to the watering process. So the facility was capped, and then in a year monitoring, we could assess that in the unsaturated part, the resistivity variation was plus 25%. So it is strictly connected to the variation in water content in the soil. In this site, we will perform core samples data to relate in laboratory the resistivity value and the water content value to convert the resistivity into an estimation of water content. There, the situation is really homogeneous, so the soil is really homogeneous, so that this correlation can be really effective.
Other questions in the front?
I have a question to IMS. So, yeah, many site across the world has mining below ground, like below open pit mines, and they might have a seismic networks. I'm not specifically on Tailings. So, can we correlate the magnitude of seismicity with the PGA value in a tailing dam? My objective behind is I want to assess whether there's a trigger liquefaction failure in the tailing dams in the surface because of underground mining induced seismicity, without having any issue points on the tailing dam itself, but below the ground.
Sorry, could you just repeat that last part of the question?
Mining is there in the underground mines with certain geophone networks, but there is no such geophones in the tailing dam itself. So can we correlate, the PGA value and seismicity of the intensity of the seismicity?
Yes, absolutely. So we often do this where we have a seismic network monitoring an underground system, and understanding the microseismicity in the underground system helps us also with understanding the PGV or ground motion that we record at the TSFs. So absolutely, they work well together, and we can use underground measurements to try and understand how the shaking may be influencing a TSF facility too.
Thank you. I think we have time for one more question. From the back, Malcolm.
So my question is to IMS Chart. So regarding mineral explorations, you mentioned that there are some improvements that we are doing to find some mineral explorations. So any case studies where you have found any sort of means seismic monitoring you have done and you have found some mineral?
Yeah, absolutely. We've done. We're closing in on over 100 surveys, dense network surveys for mineral exploration, and we have cases across all commodities with different successes based off what the imaging objectives were. I didn't dive into detail about using ANT or ambient noise tomography for mineral exploration. I tried to focus on the geotechnical application for tailings dams, but there's a lot of potential for ANT for mineral exploration, and I could probably run for 20 minutes, half an hour, running through various case studies. But the objectives are all very different. Sometimes it's direct targeting a mineral deposit. In other times, it's just imaging with high resolution the paleo basement between a cover sequence and the bedrock below. It just depends on the particular project's objectives. But yeah, what's fantastic is that same technology can be used on the scale of TSFs to image fluid pathways in the subsurface, and with a kind of resolution that would be useful for geotechnical applications.
Thank you. Last question.
Okay, I have one question for satellites and resistivity. Can you give us the estimate cost for satellite monitoring for the dam and resistivity the monitoring on sites.
Yeah. How much money do you have? I can answer. There's quite a wide range, not because they want to be difficult or commercially sensitive. There's quite a wide range in cost because we consider three factors. One is the size of the area. So the smaller the area, the cheaper it is, essentially speaking. Although the size is the smallest impact on the cost. The second one would be the data that we use. Some data is completely free. The one of the data sets I showed was completely free. And other satellites are commercially tasked, so you have to pay for each image. And again, that depends on the project scope. And the last point would be how many times you process the data. So if you need 1 time per year, then of course that will cost less than processing 30 times a year. So maximum, let's say the best, highest range satellite would be maybe $150,000 and down, depending on the application that you want. Other processes could be a lot cheaper than that. Maybe less than 50,000, maybe less than 20,000. It very much depends on what you need and how accurate you need the data to be. The higher the resolution, the more accurate the data. So it really depends on project scope, yeah.
That's per year, right?
That would be per year, yeah. So it's normally an annual subscription. Is a word that a client used the other day, subscription. We do call it contract, but subscription is the different way to describe it. And then that would roll on depending on how many years you want to go forward, for example. Historical analyses can be a lot cheaper than that. So just if you take the historical data, some of that's completely free data, so you just process once, so that can be extremely economical, even for very large areas. Okay, I think it's an individual question for each specific mine.
Speaking about this system for ERT monitoring, we are a technology provider, so we sell the system to the client, and then there is an annual fee for the cloud software to visualize the data, invert the data, download the report analysis, and the system has not many things that can change project to project. It's mainly the distance between the electrodes. So it's the main variable that can change, and can change the length of the cable. But I can give you an average price, but it's obviously then depend on the length of the cable, can be 50,000 euros. And then there is an annual fee that varies with the number of systems, that it's around 3,000 euros per year for one system. Then obviously if you have more systems, it can be less.
Thank you very much. I'm sorry, we have to break the Q&A then. I suggest you continue it over lunch or over the morning break. So we're going to break now for 20 minutes. Yeah. So please be back by 11:25 and we'll start the next session. Let's give a round of applause to all the presenters again.
Anche visto sulle vostre
aziendale, avevo 50 anni di esperienza, abbiamo lavorato con i lavoriamo con i tecnici.
Oh, Greta, falla fuori.
We should have a sweepstake and see what time we'll finish. Yeah.
Maybe make sure you know the contact.
Oh, okay.
Here we go. No part of the battle. Photo session. Could be a celebrity.
Yeah. I can see you right now.
Throw in you.